In this session, we're going to be talking about the auto-ionization of water, which is also called the water dissociation constant, Kw. We'll be talking about the pH scale and how to calculate the pH of strong acids and strong bases. So in a previous tutorial, we talked about how water could act as an acid and base, or another way of saying the water was actually an amphoteric. So that's where we actually really going to start out with. So if I have two water molecules, liquid, and if they react together, and that's actually how it happens in case of pure water, the water we actually drink. So when those two water molecules react, they will set up an equilibrium to make H3O plus aqueous and OH minus aqueous. So another way of saying this H3O plus and OH minus is coming from those two water molecules where one of them is acting as an acid and the other one is acting as a base. So if I want to take an example here, just doesn't matter which one you pick, and I just pick this left water molecule, and pair up with this OH minus here. So you can clearly see here how this is losing the proton. So if it's losing the proton, it's acting as an acid. It's a proton donor. And on the other hand, OH minus is going to be called a conjugate base there. And that's what the bases are. The OH minus production gives you the amount of base you have in there. And then obviously the other one, the H2O, making the H3O plus, that means it must be acting as a base, and whatever it makes on the other side, which is H3O plus, is going to be called a conjugate acid. Okay, so this is how typically the water exists as. It's not just going to be H2O all the time. You may have a very small amount of H3O plus and the OH minus present in the water. It's so small that you really never notice. Okay, and when I'm writing the Kw, or the water dissociation constant here, it's actually going to be the concentration of H3O plus times the concentration of OH minus, and we don't really include the concentrations of the reactants here because they are in liquid form. So just keep in mind, you only write down these constant expressions if something is either an aqueous or in a gaseous. So for right now, just know the Kw is the multiplication of the hydronium ion concentration and the OH minus ion concentration. That's one way of writing it. And sure, you may see this written in the books as H plus concentration times the OH minus concentration, and they are both the same thing. Okay, well, in addition to that, the Kw is actually constant for the most part. The value of Kw is going to be 10 to the minus 14. It is a little bit of temperature sensitive, and it changes slightly with the temperature. If they don't tell you anything about it, just assume just take it as 10 to the minus 14. If they tell you an extra and a special value for the Kw, that's when you want to use that one. But for the rest of the part, just use 10 to the minus 14. Okay, so then if I want to go ahead and set this up equal to the concentration of H3O plus and the OH minus here, and when I'm trying to figure out what the value is going to be for this H3O plus and OH minus, and logically, if I go back to my equation and talk about the H3O plus concentration and the OH minus concentration, there's two things going on. They're coming from the same source. They're coming from the water, and they are 1-to-1 mole ratio, which means if you make 1 mole of H3O plus, you should be making 1 mole of OH minus. Or another way of saying, in pure water, the concentration of H3O plus and the OH minus is actually the same. And how's that same? Well, we can set those equal to, assume they're both going to be X. All right, so if they are both x, then you just figure out what x squared equal to 10 to the minus 14 gonna be here, and then you take the square root on both sides, and then this x is gonna come out to be 10 to the minus 7 molar. So that's the concentration gonna be for both your H3O plus and the OH minus in pure water. Anytime you have the concentration of these two ions to be 10 to the minus 7, we are sitting at neutral conditions, or another way of saying we are sitting in water, or pure water rather. So this is where that scale comes in right here. So the pH scale, I'm pretty sure a lot of you are familiar with how that really works. And the pH more or less measures how much water how much concentrations of the acid or the base you have in a particular given solution. And if let's start out with the neutral. So neutral is when you are looking at the pH of 7. All right. So at neutral, when I'm looking at my concentration of H3O plus and OH minus, they have to be equal to one another. Okay. And as you move to the left, or another way of saying to the acidic side, or to the right, or another way of saying to the basic side, the concentration of H3O plus and the OH minus changes accordingly. So they actually have an inversal relation where if the concentration of hydronium ion goes up, the concentration of OH minus goes down. So another way of saying, if I'm at the acidic conditions, which means I need to have more concentration for the hydronium ion, so I can say the concentration of H3O plus on to the left side is actually going to be greater than the concentration of OH minus. All right, and the opposite will happen onto the right side, where the concentration of OH minus is actually bigger than the concentration of H3O plus. And how do they really change? It all is going to be dependent on this Kw equation. So keep in mind this Kw, which is the concentration of H3O plus times the OH minus, that's how they're going to be relating to one another. So if you change one of them, the other one will change accordingly, so that this equation always stays true. So that's why they are inverse in relation with one another. Okay, so I do want to talk a little bit about the pH scale here. A lot of you are already familiar with the pH scale. So if you are closer to the 0 here, so there's supposed to be 0 right there. If you're closer to the 0, that means you are very acidic. As you go toward the 7, the acidity kind of decreases. All right, and then right at 7, you are neutral. And after you go away from 7 toward the 14, your basicity increases. And I do have different colors here. That just means if your solution is very acidic, your litmus paper or the pH paper is actually going to be very red, um, anywhere between 0 to 3, let's say, not maybe even 3, maybe 0 to 2.5, it's going to be fairly red, and then it's going to start changing to like a pinkish color until it reaches 7. So it's some of the really good examples. Gastric juice, which is the pH of the stomach, is anywhere between 1 and 2. Soft drinks usually lies around 3 pH, fairly acidic. Coffee has a pH of 5. Urine has a pH of 6. Milk has a pH about 6.4. And obviously, when we turn into the neutral, your pH paper turns green, a light green rather, and also you can talk about litmus paper, so that's why I have this color obviously with a green. And then as you go on to the basic side, the green color deepens. So blood plasma, obviously one of the big examples there, it's slightly basic. So I have this green color to be deepened a little bit. And as you go down, let's talk about milk and magnesia. It's very dark green color because it's fairly basic, but as you go further down onto the scale, it literally the color of litmus paper in those solutions literally changes from green, dark green to light blue to dark blue. So that's why this bleach, I have made that in like a blue color. And we talk about maybe 1 molar NaOH. That's going to be very basic, and it's actually the litmus paper color is going to be very dark blue in this particular case. Okay, so that's your pH scale. You want to have a rough idea of obviously where the things are, just especially the one you use in everyday life. Bleach, everyone uses it, coffee, soft drink, everyone should know about urine, gastric juice, and obviously know the relation of the concentration of hydronium ion and the OH minus when you're going from one pH to another pH. Okay, well, that's all about the KW. Well, let's talk about how you calculate the pH and the POH. The definition of pH is going to be actually negative log of H plus, or a negative log of H3O plus. So it's kind of same thing. And then the definition of POH is going to be negative log of OH minus. Okay, and obviously these definitions literally coming from the KWs. I don't want to derive those equations, but make sure you are aware of these equations here. In addition to that, you also want to know the pH plus POH is actually going to be equal to 14. So you have maybe 3 formulas here to you want to be aware of. Obviously, know the KW expression, know the pH definition, the POH definition, and the relation between the pH and the POH. Okay, well, now let's use those definitions and figure out the pH of maybe in a strong acid or strong base. Now here I'm only going to be talking about the pH of strong acids and strong bases. That's because it's literally very easy to figure out their pHs. However, the weak acids and weak bases all have a separate tutorial where I talk about how to calculate the pH and the POH. It's a little bit complicated. Okay, so let's look at the first question here. Calculate the pH of 0.5 molar HBr. Okay, well, the very first thing you want to ask yourself when you're doing these questions is this is an acid or a base. And a lot of time students forget to ask those basic questions and they will get confused when you're solving these problems. Obviously, this is an acid, okay? And the next question you want to ask yourself if it's in a strong acid or weak acid. And like I said in this tutorial, we're only worrying about strong acids, so it's going to be a strong acid. And what do we know about strong acids? Well, strong acids will break into ions completely. So whether I write it like HBr aqueous breaking into H plus and Br minus, that's one way of writing it obviously, or I write it like HBr aqueous plus water, and that's going on to make H3O plus and Br minus. Both of the ways are going to be fine, and at the end of the day, the most important thing you're going to be looking when you're trying to determine the pH or even the POH is what's going to be the H plus concentration, H3O plus concentration, or the OH minus concentration. Obviously, the H plus concentration and the H3O plus concentrations literally means the same thing. So, since this breaks into ions completely, the concentration of H plus or H3O plus at the end of the day is going to be 0.5 molar because it's a monoprotic acid and it's a 1-to-1 mole ratio throughout. So I know the H plus concentration we have here is 0.5 molar, and once you know either the H plus or OH minus, it's easy to calculate the pH. All we really got to do is negative log of 0.5. Okay, and when you take the negative log of 0.5, I believe it's going to be somewhere about 0.7. Let me just double check. Oh, so negative log of 0.5 is actually 0.3. Okay, so that's going to be the pH. This is very acidic because the pH is very, fairly close to 0 here. Okay, let's look at the second question here. It's asking to calculate the hydronium ion concentration, which is H3O plus, and the pH of barium hydroxide there. Okay, there's a few ways you can do these type of problems here. So first of all, know what this barium hydroxide is. Is this an acid or a base? Okay, so once you figure out that it's in a base because it's in a hydroxide, figure out if it's in a strong or a weak. That's the next question you want to ask yourself. And it is in a strong base. What that really means, this base, when dissolved in water, it's going to break completely into Ba2 plus and 2OH minus ion there. Okay, and then figure out what the concentration gonna be for, in this case, the OH minus. You don't really have to worry about what the concentration of Ba2 plus is, because when you're doing the pHs, you only worry about either H plus or the OH minus. So if you're starting out with the 0.5 molar here and you lose all of that, so you lose all of this, how much of barium 2 plus are you going to make, and how much of hydroxide are you going to make? Well, barium 2 plus is a 1-to-1 mole ratio, and it's going to be 0.5, but what we're really worrying about is OH minus, so it should be 0.5 times 2, which is going to be 1.0 molar, because it's a 1-to-2 mole ratio, so that's why we multiply that by 2. So now I know the OH minus concentration is 1.0 molar. So there's a couple of things you can do here to find the pH, and obviously the hydronium ion as well. If you want to find the hydronium ion here, the best thing to do would be use H3O plus concentration times the OH minus concentration, which is 1.0 molar, is going to be equal to the 10 to the minus 14. So you're really using the Kw expression. So the H3O plus here is going to be 10 to the minus 14 divided by 1, which is still going to be 10 to the minus 14. So that's one of your answers here. And obviously, once you know that, you can literally calculate the pH here. And I can do pH equals negative log of 10 to the minus 14, which is going to be coming out to be 14. So it's very basic in nature here. If you don't want to calculate the H3O plus concentration and just strictly get the pH straight from the OH, you can also calculate the pOH first, which is going to be negative log of the OH minus, which is 1.0. So that's figure out what the negative log going to be for 1, and that's going to be 0 actually. And then use pH plus pOH equal to 14 as your next equation here. So pH plus 0 equal to 14 gives you pH to be 14. So there's different ways you can do these problems, and either one of these ways are going to be okay. All right, so in this session, remember what we learned. We learned about how to calculate the pH of strong acids and strong bases. Obviously, it comes down to knowing either the H plus concentration or the OH minus concentration. In addition to that, be able to use this Kw expression to find either the H3O plus or the OH minus when one of them is going to be given. All right, so if you have any questions about this, feel free to leave any comments in the section below.